Bismillahirrahmanirrahim. Assalamu alaikum, students. Today we are going to discuss another topic. Today's topic is the crystalline state. So this is our today's topic. Let me underline it. So we are going to discuss some basic definitions used in the study of crystals. So let us start. The crystalline state. You know, to the naked eye, if we have some solid, it appears as a continuous, rigid body. But experiments have proved, however, that all solids are composed of discrete basic units. We call them atoms, right? And these atoms are not distributed randomly, but are arranged in a highly ordered manner relative to each other, right? Now, such a group of ordered atoms is referred to as a crystal, right? Let me underline it. So when we say crystal, by that we mean we have a group of ordered atoms, right? Now there are several types of crystalline structure depending on the geometry of the atomic arrangement. And a knowledge of these is important in solid state physics because these structures usually influence the physical properties of solids. I repeat, the arrangement of atoms in a solid or the geometry of the crystalline structure in a solid affects or influences the physical properties of solids, right? You need to understand that. And in some solids, atoms are randomly arranged. Randomly arranged, right? That is, crystalline structure is absent in some solids, right? And such non-crystalline solids are called amorphous solids, right? So when we say we have an amorphous solid, by that we mean in this solid, atoms are randomly arranged, crystalline structure is absent in this solid, right? Now, a solid is said to be a crystal, as we said, if the atoms are arranged in such a way that their positions are exactly periodic. Let me write it. These definitions you need to remember. A solid is said to be a crystal if the atoms are arranged in such a way that their positions are exactly periodic. So you need to remember this. When we say solid is crystal, that means its atoms are arranged in such a way that their positions are exactly periodic, right? That's what is the meaning of ordered atoms, right? I will draw a figure that will illustrate the concept. Let me draw the figure first. Use another color. Let me name it figure 1. So let me use some other color, this one. So this figure 1 shows a crystalline solid. As you can see, all the atoms, these dots are showing the atoms in the solid, and you can see all the atoms which we have shown are arranged periodically, right? And we are talking in 2 dimensions. This is a 2-dimensional figure of a solid, but that is true in 3 dimensions as well. So let this be x-axis, this be y-axis. Let me name some points to move forward. I name this site A, this B, and this site C. And let this distance be small a, and let this distance be small b. So the distance between any 2 nearest neighbors along the axis x direction is a. So what's a? It is distance between any 2 nearest neighbors along the x direction, right? So this is a, this is also 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 a. and same goes for all such distances between nearest neighbors along x-axis. And b is what? It is the distance between any two nearest neighbors along y direction, right? So this is b, this is b, this is b, this is b, all such distances are b, right? And you need to remember that x and y axes are not necessarily orthogonal. X and y axes are not necessarily let me clear it. Necessarily orthogonal, that is perpendicular. It's not necessary, right? Now, a perfect crystal maintains this periodicity or repetitivity in both the x and y directions from minus infinity to plus infinity, right? Let me write it in other color. You need to remember this. A perfect crystal maintains this periodicity or this repetition, that is its repetitivity in both x and y directions from minus infinity to plus infinity, right? So this is what we mean by a perfect crystal. So when I say I have a perfect crystal, by that I mean the periodicity in the arrangement extends in x and y, and when we talk of 3 dimensions, that extends in z direction as well, from minus infinity to plus infinity, right? Now you can see I have named 3 atoms A, B, and C, and when there is periodicity, that means the atoms A, B, C, etc., that means all the atoms are equivalent, right? So from periodicity, it follows from the periodicity means pattern is repetitive, it repeats, and it follows from the periodicity that the atoms A, B, C, which we have labeled, and all others, etc., are equivalent, right? What is the meaning of that? That means to an observer located at any of these atomic sites, the crystal appears exactly the same. I repeat, When I say due to periodicity, all atoms like ABC and all others shown are equivalent, by that what I mean? I mean to an observer located at any of these atomic sites, the crystal appears exactly the same. Now, the same idea is often expressed by saying that a crystal possesses a translational symmetry. A crystal possesses a translational symmetry, meaning that if a crystal is translated by any vector joining two atoms, let us show a vector in the figure. For example, I show vector in this color. I show this vector, some vector. This vector joins atom A and C. For example, you can take any vector joining two atoms. We name it R, right? So let us move to the idea of translational symmetry. We are saying that a crystal possesses a translational symmetry, meaning that if the crystal is translated by any vector joining two atoms, joining two atoms, say vector R in figure 1, the crystal appears exactly the same as it did before the translation. Try to understand it. I am saying crystal possesses a translational symmetry. And by that I am saying that it means that if the crystal is translated by any vector joining two atoms, as we have shown one vector R joining A and C, if we translate the whole crystal by this vector, that means we move this point to this point. Relatively all other points will be shifted, but because of that translation, there will be no impact on the appearance of the crystal. That's what we have written. That translation symmetry means if the crystal is translated by any vector joining two atoms, say R in figure 1, the crystal appears exactly the same as it did before the translation, right? So in other words, the crystal remains invariant under any such translation, right? So let us move forward. Now, strictly speaking, now let us move to now the realistic picture. Strictly speaking, one cannot cannot prepare a perfect crystal. Why? Some reasons may be obvious to you. I'm saying one cannot prepare a perfect crystal. Reasons. First, you know, the surface of a crystal is a kind of imperfection because the periodicity is interrupted there. So let me write the surface of a crystal is a kind of imperfection because the periodicity is interrupted there. So the atoms near the surface see an environment different from the environment seen by atoms deep within the crystal, and as a result behave differently. So this is one reason, because we have ultimately crystal has a surface, and at the surface periodicity is interpreted. So environment of surface atoms is different from the environment of the atoms deep within the crystal. So due to this reason, we cannot have a perfect crystal. So let's move to the second reason. You know, there are thermal vibrations of the atoms around their equilibrium positions for any temperature T greater than 0 degree Kelvin. Inside a solid, at any temperature greater than 0 degree Kelvin, atoms vibrate around their equilibrium positions. Now, because of these vibrations, the crystal is always distorted to a lesser or greater degree depending on temperature T. Let me write it. Because of thermal vibrations, the crystal is always distorted to a lesser or greater degree depending on temperature T, right? Now, third reason why we cannot have a perfect crystal. An actual crystal always contains some foreign atoms. An actual crystal always contains some foreign atoms, which we call impurities. Right? Even with the best crystal growing techniques, some impurities remain, which spoils the perfect crystal structure. Notwithstanding these difficulties, one can prepare crystals such that the effects of imperfections on the phenomena being studied are extremely minor. For example, one can isolate a sodium crystal so large, approximately 1 cubic centimeter, that the ratio of surface atoms to all atoms is small, and the crystal is pure enough so that impurities are negligible. And at temperatures that are low enough, lattice vibrations are weak, so weak that the effects of all these imperfections on, say, the optical properties of the sodium sample are negligible. So it is in this split that we speak of a perfect crystal. Which split? That we can have a sizable crystal in which we can minimize the effects we stated A, B, and C on the crystal, right? When we study them. Now, imperfections themselves are often the main object of interest. Another point you need to remember, imperfections themselves are often the main object of interest. How? For example, the thermal vibrations of the atoms are the main source of electrical resistivity in metals, right? So when this is the case, one does not abandon the crystal concept entirely, but treats the imperfection or imperfections of interest as a small perturbation in the crystalline structure, right? You need to remember that many of the most interesting phenomena in solids are associated with imperfections. I think this is all for today. So we introduced this crystalline state today. Go through all the lectures. Don't waste your time. And don't forget to like, subscribe, and share my channel. You can comment in the comment box. Thank you. God bless you. Assalamu alaikum.